So I meant to just pause, I accidentally stopped, so I think I'm ready to go. Go ahead and there we go. Alright, so the second problem. Let's read through the statement of the second problem. An infinitely long uniform rod. Let me see if I can get this to see. No, these buttons are not working for me. Huh. Alright, so again, we'll do it the old-fashioned way. Got to refocus there. Oh, that's not good focus, is it? Let's try that again. Alright. An infinitely long uniform rod of mass mu per unit length is situated on the z-axis. The gravitational force on the mass m at a distance rho from the z-axis is given this expression right here. Alright. Also, the components of the del operator are given in this expression for the gradient. You can figure it out from that. So for part A, I want you to rewrite the force in rectangular coordinates and show that the curl of the force is 0. Then for part B, I want you to show the curl of the force is also 0 in cylindrical coordinates. And then for part C, I want you to explain why all conditions for the conservative force have been held by this force. And lastly, I want you to find the potential energy associated with this force. Okay. Alright. So for part A, I was asked to rewrite the force in rectangular coordinates. Alright, so let's just remember that the force that I was given is minus 2gm mu over rho hat. And there's a very quick way to do this, but I would just as soon, and by the way, the quick way would be to, I'll show you the quick way, why not? Rho squared rho vector. So got this sort of coordinate system here, and rho just sort of lays, it's always perpendicular to the z-axis, so I can draw it here kind of laying in the xy plane if I want to, so it's sort of laying there, and here's that azimuthal angle phi here. Alright, and so this vector rho, which has a magnitude rho and is in the rho hat direction, it has an x component that is equal to rho cosine theta and a y component that is here. But clearly, rho squared is equal to x squared plus y squared, and rho is equal to x hat. Well, I'll just go ahead and write that out. Rho, the rho vector. Well, let me just say the r vector. Let's do it that way. Is equal to rho and the rho hat. In this case, because there's no z component, so that's just a cylindrical thing. And it also happens to be equal to in rectangular coordinates x in the x hat plus y in the y hat. Also, let's note that the rho squared, the distance from the x-axis squared, must be equal to x squared plus y squared. And then I'm really ready to do my substitution. Minus 2gm mu over rho squared, x squared plus y squared. Let me pause my video. Alright, so let's get back to that. Okay, so anyway, I could just make the substitution wherever I see rho squared of x squared plus y squared, and where I see the rho vector, I can note that that is x hat plus y hat. However, I don't think that this is the way anybody did the problem, so I'll show you the way that is a little bit more intuitive to do the problem, which is to use it in this form and do substitutions, not this one. Alright, so in that form, let's go ahead and do some substitutions. In that form, I notice that rho must be equal to, I've got my rho vector here, rho cosine of phi in the x direction, plus rho sine phi in the y direction. Okay, and rho itself, in terms of x and y, is equal to the square root of x squared plus y squared. And obviously cosine phi is equal to x over rho, and sine phi is equal to y over rho. Okay, so I think now we're probably sort of in decent shape, although the rho hat direction would be, sorry, that should say rho times rho hat. That's what I should have written there. Okay, so since rho times rho hat is equal to this, which in this particular case is equal to the r vector, then if I divide both sides by rho, you'll see that rho hat is just equal to cosine phi in the x direction plus sine phi in the y direction. This is the type of work that I saw mostly. So now I'm ready to go ahead and make some substitution here. So I've got my expression for a force up here in terms of cylindrical coordinates. So I've got minus 2g m mu over rho, which is x squared plus y squared quantity square rooted, so I'll write that as 2 to the 1/2, times the rho hat vector, which is cosine phi plus sine phi, where cosine phi is x over rho, and sine phi is y over rho, the y hat. So I'm not all the way there, because now I'll have to remember that wherever I see a rho, it's also the square root of x squared plus y squared. So my expression is 2g m mu over, both of these have an x squared plus y squared quantity square rooted in the denominator, so I'll get x squared plus y squared here, and times the quantity x hat plus y hat. And that's the same expression that we got before, using the types of relations that I saw on most of your papers. So that's supposed to be lowercase m. All right. So that was part of the question. Let's get back to what the question was. Rewrite f in rectangular coordinates. Show that the curl f is 0. And using those rectangular coordinates. So let's do that. The curl of f is equal to the 3 by 3 determinant of x hat, y hat, z hat, d dx, partial dy, partial dz, acting on fx, fy, and fz, so I'll need to go ahead and make that substitution, minus, you know what, let's put that out front, minus, I'll put that after it, times negative 2g m mu. Alright, so in that case I've got x times x squared plus y squared to the negative 1. And for my y component I've got y times, let me shut that off. Okay. Y times x squared plus y squared to the negative 1, and my z component is 0. Alright, so my curl, I put my minus sign out there. So I've got a negative 2g m mu times x hat times the partial of 0 with respect to y, partial of this function with respect to z. This function does not depend on z at all, so I've got a 0 there. Minus y hat times the partial of x, the partial of 0 with respect to x, which is obviously 0, minus the partial with respect to z of this object, which has no z in it, so I'll put a 0 there as well, and plus z hat times, okay, this one will be a little bit trickier, partial with respect to x of the quantity y, x squared plus y squared to the minus 1, minus partial with respect to y acting on the quantity x times x squared plus y squared to the minus 1. And I need to put a curly bracket to show that the whole term there is together. I wish that would be a little list for you. Alright. Okay. So, let's go ahead then and do it. So I only have a z hat component that remains. So let's go ahead and solve for it. So I've got minus 2g m mu z hat times the quantity. Partial with respect to that. Well, I got the partial with respect to x of this object. Y is going to behave like a constant, so it can come out front. And then I just have partial with respect to that object, which is negative 1 times x squared plus y squared to the negative 2 by the chain rule, and times 2x. Minus partial with respect to y, so the x is going to act like a constant and come out front. Negative 1 x squared plus y squared to the negative 2 times 2y. This is turning out quite yucky. So let's go ahead and do our next line. Minus 2g m mu z hat times negative 2xy x squared plus y squared to the minus 2 plus 2xy x squared plus y squared to the negative 2. And those cancel out, so I get 0. Oh, and I should have named my starting point here, which is a definition of curl. This one is harder to name my starting point. That cylindrical coordinates one. Not sure quite what I would call that. Alright, so, because it's kind of just math, it's kind of okay to not give it a name. Alright, so let's go ahead then and start part 2. Show that the curl of f is 0 in cylindrical coordinates. So let's do that. So in cylindrical coordinates, we already have our expression for f given in the statement of the question. So we don't have to make any changes there. Rho hat, phi hat, z hat. Those are the three directions in cylindrical coordinates. d rho, d phi, d z. Those are the three components of the del operator. And actually, I've got an error here. 1 over rho should be here. So I just want to show you that came from here. It was given on my problem. Okay. And I think that's all I needed. All right. So my rho component is minus 2gm mu over rho. My phi hat component 0. My z hat component is 0. So I have to do that. Definition of curl. Alright. So I've got rho hat times partial with respect to phi acting on 0 gives me 0, so 1 over rho times that is also equal to 0, minus partial of 0 with respect to z, so both of those are 0, minus phi hat times partial of 0 with respect to rho is 0. This object has no z in it, so its partial with respect to z is also 0, so that's 0, plus z hat. Partial of 0 with respect to rho, 0. And 1 over rho times the partial of this object with respect to phi, where this object does not depend on phi. That's also a 0. So that gave me 0. Good enough. Okay. Part C of the question. Explain why all conditions for the conservative force are held by this force. There are two conditions for the conservative force. So for a force to be conservative. Alright, so the first one is that the force can be expressed as a function of location. in this case, is that true? Of course it is, because I'm given this expression, which is in itself obviously a function of location. All right, so check. Yes, does it? All right, so then the second condition it must meet is that the work done by the force in moving an object from location A to location B must not depend on the path. All right. And so in order to show that is the case, I'm not going to do a proof. What I'm going to do is I'm going to use a condition that I know, which is that if this will hold, if and only if the cross product, the curl of the force is equal to 0. So that means that the curl of force is equal to 0. That condition will hold. All right, so in this case, I've already found that the curl of the force was equal to 0. So the work done by the force in moving objects from A to B will not be a function of path. And check. All right, so those are the two conditions, and that's how they are held by this force. Okay, so indeed this is a conservative force. Now I can find the potential energy associated with the force. Let me do that. I need a drink of water again, so let me pause this thing. All right. Close that down. Okay. All right, so the last part here. Find the potential energy as a function of R. Let's do that. My paper's in order here. All right. All right, so in this case, if I go from an arbitrary point A to another arbitrary point B, since it doesn't depend on path, and let's have this be the z-axis, I will choose to go along the r hat direction out to row B, the rho hat direction out to row B, and then I will go along the z hat direction up to ZB, and then I can go along the phi hat direction out to my point B. All right, noticing that these two portions of the path, oh, that's not on there. All right, so I chose to go out the rho hat direction to row B, up the z hat direction to ZB, and then along the phi hat direction to the point B. So I know that for these parts of the path that are in the z hat and phi hat direction, the dot product, I'm sorry, let me go ahead and write out my expression for potential energy. In this case, the force is the gravitational force, dot dr. Okay. So, and this doesn't depend on path, so I'm choosing to go along these three, noting that my dot product will be 0 along these other two, only the rho hat part of the walk will be included. So here I'm letting point A be my R naught point, the point where I'm sort of defining that this is sort of a point where the potential energy is some constant, and my point B is going to be what I'm calling R. Okay, so I've got minus rho naught to rho, because I'm only going to have to think about this part of the path. And FG row component is obviously negative 2g mu over rho times d rho. Okay. So I've got my minus signs are going to cancel each other. 2g mu 1 over rho d rho. That gives me natural log of rho, which I have to evaluate from rho naught to rho. So that gives me 2g mu natural log of rho over rho naught. And that's what I've got. Okay. Alright, so that's the solution, and I will see you guys tomorrow. We'll talk about the rubric in class.